Recording in progress.
Morning, everyone. How are you all doing today? Oh my, so it's middle of March here, and we're actually getting some warm weather. Let's see, to us we're all the way up in the 80s today, Fahrenheit, which for the rest of the world would be, I guess, in the upper 20s? So unseasonably warm here. So I'm actually wearing shorts for the first time this year. Can't see them, of course. How are y'all doing today? I can't talk this morning. How are all of you today? Good morning from California. Hello to the UK. And where else are you from? Well, what I've got for you today is, how should I put this? We're going to go through the next chapter pretty quickly. These are counting problems, how to compute or calculate how many things fit a certain criteria. It's going to involve things like combinations, permutations, product rule, sum rule, exclusion principle, and the pigeonhole principle. So what I've got for you is a series of problems. If you're one of my students, you can go onto our class website. I have two, they're listed as quizzes. They're really just assignments. And the reason they're quizzes is because the system can automatically evaluate whether you got the correct answer or not. So we're going to do the practice problems today, and then for homework you're going to do the other set of problems. So I think there's about 12 or so practice problems, and then there's 10 problems that you need to do. So we'll go over the practice problems during what would normally be our lecture time, and then I'll stick around for a little while afterwards for you to go over the other problems yourself. And if you have any questions, you can just hop on and you can ask those. So why don't we go ahead and get started. These are the practice problems we've got. All you have to do is click on Take the Quiz and we can get going on this. So, product and sum rule. This is two ways to count the number of things. The product rule can be used in cases where you need to multiply some answers, some values together. And of course, sum rule is used where you need to add them together. And one way to think about it is if the things you need to do can be connected with the word and, it probably means you need to multiply them. And if they can be connected together with the word or, it might mean that you can add them together. If you remember many weeks ago, I think I did that for you. I kind of went over this table where I showed the different disciplines, like you have logic and Boolean algebra, programming, and then arithmetic. And I said that all these operations are kind of the same. And so and is a lot like multiply, and or is a lot like add. Hold on a sec here. All right. So the first question we have here is, how many integers, I'll zoom in a bit, how many integers between 100 and 1,000 have three distinct odd digits, three unique odd digits? For example, 953 and 371 are two such numbers, but 737 and 199 are not, because they have repeated digits in them, even though they're all odd. So how would you compute this? How would you calculate how many numbers between 100 and 1,000 have distinct odd digits? Do you want to try that problem yourself and then post in the chat when you think you've got an answer? And then we'll go over it. And if you've already got that problem, we can work on the next one. Harry wants to read a book. His bookshelf has 14 novels, 15 biographies, and 13 mysteries. How many choices does he have? In some of these problems, the numbers have been randomized. So if you're going through the problems yourself, you may have a slightly different set of values. You'll work out the problem the same way, using the same techniques. You'll just have different numbers. So try these two problems. Question number one, how many integers between 100 and 1,000 have three distinct odd digits? And then question number two, Harry wants to read a book. His bookshelf has 14 novels, 15 biographies, and 13 mysteries. How many choices does he have? What do you think the answers are? Okay, maybe I'll give you another minute. Okay, let's see how to work out that problem. So you can kind of think of this as there are 3-digit positions that you need to fill in. There's the first position, the second position, and the third position. So instead of thinking about it as a number, think about it as maybe an array of digits, to use like a programmer analogy. You have a first position to fill in, a second position to fill in, and a third position to fill in. So in the first position, there are 5 possible numbers you could put there. You could put a 1, a 3, a 5, a 7, or a 9. So there are 5 possibilities for the first position. In the second position, there are only 4 possibilities because you already used one of them for the first one. So no matter what number you picked for the first position, you can't use that number for the second one. So that leaves only 4 possibilities left. And then for the third position, there's only 3 numbers left that you can use because you already used 2 of them for the first 2 positions. So you've got 5 in the first position, and 4 in the second position, and 3 in the third position. That means you're going to multiply these together. 5 times 4 times 3 is 60. So there are 60 integers between 100 and 1,000 that have 3 digits, all of them odd, and they're all different from each other. Number 2, again, was Harry wants to read a book. There are 14 novels, 15 biographies, and 13 mysteries he can pick from. How many choices does he have? So this is one where he could pick from 14 novels. He could pick one of 14 novels, or he could pick one of 15 biographies, or he could pick one of 13 mysteries. 14 plus 15 plus 13 is 30, no, 40, what is this, 42? If I did my math correctly. There are 42 possible books for him to pick from. He can pick any one of those 42. Let's go on and do question number 3. Number 3, 2 people from a group of 54 will represent your company at a national conference. One person will be the primary speaker, the other will be the backup. How many possible pairs of representatives are there? And let me see if I can squeeze number 4 onto the screen so you can look at both of them at once. Kim needs to go from Sacramento to San Jose, but she can't drive. However, she can take any of 10 trains or 3 buses to go to San Francisco, and then from there she can choose among 11 trains or 7 buses to go to San Jose. How many ways are there for Kim to get to her destination? So again, maybe I'll give you a couple minutes. Take a look at these 2 problems and see if you can figure out the answers. Now, these are going to be using the same techniques that we did for the first 2 problems. So see if you can answer them yourself.
Sorry, I just joined a bit late. Is this the practice or the counting problems?
This is the practice.
Okay, thank you.
And your questions, they'll be the same questions, but your numbers might be slightly different because the system randomizes them. So you'll recognize the words, but the numbers might be a little bit different.
Okay, good to know.
Let's see, you got 50 for number 4. I think the answer is going to be a little bit higher than that. Actually, not a little bit higher. It'll be much higher than that. So let's take a look at these two problems. For number 3, 2 people from a group of 54. So there's going to be a primary speaker and a backup speaker. That means there's going to be 2 positions to fill. You got your primary position and your backup position. How many possible people could fill that first position? Only one person can fill it, right? But how many possible people could we choose from to fill that first position? Well, there's 54 people in the company. So 54 possible people could fill, one of 54 people could fill that first position. And then in the second position, the backup person, well, obviously won't be the primary person, so there's only 53 people left who could fill that position. So we're going to have a primary speaker and a backup speaker, which means we multiply these together. So 54 times 53 is 2,862 possible pairings of people who would go and give a talk at this conference. And then number 4, Sacramento to San Jose. So in this one, Kim is going to start from Sacramento and is going to go travel to San Francisco, and then from there is going to go to San Jose. Actually, I didn't draw this picture very topologically correctly. Right? Now for those of you who are not in California, California is roughly shaped like this, right? Here we are in Sacramento, and then San Francisco is here, and then San Jose is down here. So that's how you'd make that trip. Okay, so if you start at Sacramento, there are 10 trains she could take. So she could take one of 10 trains or 3 buses. So there's 10 trains, 3 buses. So she could take any one of these. She could take any one of these 10 trains, or she could take one of these 3 buses. So there's a total of 13 possible ways to get from Sacramento to San Francisco. And then from San Francisco to San Jose, she could take, 11 trains, or she could take 7 buses. So there are 11 plus 7 ways to get from San Francisco to San Jose. Okay, so she's going to take one of these 13 routes, or one of these 13 ways to do the first leg of her journey, and then she's going to do one of 18 ways to do the second leg of her journey, which means there are 13 times 18 possible ways to make her trip. See, 13 times 18 is 234. Actually, I should be entering these answers as we go. So here I got 60. This one, number 2, I got 42. Number 3, I got 2862. And for 4, I got 234. Okay. So this next section is called the inclusion-exclusion principle. It's another way of counting things. So in this question, we have two bus routes, bus route A and B. Bus route A has 23 stops, bus route B has 26 stops, and the two routes overlap at 7 stops. How many stops are there altogether? So the picture kind of looks like this. We got bus route A, we got bus route B, and you can see they overlap here at 7 places. So if we were just to add 23 and 26 together, we would get 49, but that would end up counting those 7 overlap stops twice. We'd count them once in the 23, and we count them again in the 26. So really we want to add them together, but we want to subtract off one of those sets of duplicates. You kind of think of this as being one of these Venn diagrams. Here's route A, and here's route B, and there's the 23 stops in A, and there's the 26 stops in B, and then right here in that overlap area, 7 of those stops get counted twice. So to solve this problem, you take the 23 from A, you add the 26 from B, and then you subtract off one of the sets of duplicates. Let's see, 23 plus 26 is 49, and then we take away 7, and we end up with 42. Another nice number. So another way to think about this in terms of sets is we take the two sets and we join them together using union, and then we subtract off the one of the sets of intersections. And then the size of that set is what we're looking for. So let's put in 42 here. Next question. A class of 32 students were surveyed about programming languages. And it says nothing here about them all being computer science students. It's just a class of students. 15 said that they had used Java. 12 said they had used Python. 9 had used both. How many students hadn't used any? So here's what this problem looks like. You got the 15 used Java, 12 used Python, 9 used both, and there's a total of 32. So I imagine there's some kind of like survey here, and you just check the box if you've used that language. So some people have only checked Java. Some have checked both boxes. Some maybe only checked Python, and some didn't check any. Again, this is inclusion-exclusion. Can you figure out the answer to this one? So remember, some people have only used one, some have used both, and some have used none at all. Have you got it? So to solve this problem, we're going to take the people that have used Java, which is 15. We'll add the people who have used Python, but those count the people that have used both twice. So we need to take off one of those sets of duplicates. So the amount of people that have used both is 9. So 15 plus 12 minus 9 is 27 minus 9, which is 18. So a total of 18 people had used some programming language. There's a total of 32 people in the class. How many people use none? 32 minus 18 is 14. So there's the answer. Okay, permutations. You've heard this word before, although sometimes the words permutations and combinations are kind of mixed up. Specifically, permutations. In permutations, the order of the items matters. In combinations, the order does not matter. Now, I know that there's a formula for doing permutations, but the formula is actually just a way to solve these problems. I want to focus more on the concept of trying to figure out how many permutations are there, how would you calculate the number if you didn't have the formula, and then we'll see how the formula can help you. So in question number 7, how many ways are there to rearrange the letters in the word match? And before we try to figure out how to calculate that answer, let's try to take a look at some ways we could do it. One way we could do it is we could just simply enumerate all of the possible words or rearrangement of the letters and just count them up. The other is we could figure out if there's some way to more directly calculate the answer, like plug it into some kind of formula. But let's try it the first way first. Let's say we had the word for. F-O-R. How many ways are there to rearrange the letters in this word? Well, there's 3 possible letters, so there's 3 positions to fill. In the first position, we could pick from any one of those 3 letters. It could be O or F or R. Actually, let me do it this way. Let's just go ahead and rearrange all the letters. So one way to rearrange them is F-O-R. Another one would be F-R-O. And then there would be R-O-F. And RFO, and then finally ORF and OFR. So there are 6 ways to rearrange all the letters of the word for. And all we do is we just list them all out and then just count them up. But to calculate the answer, we see that there are 3 possible letters to fill, a first letter, a second letter, and a third letter. There are 3 possible letters we could put in that first position. We could put either F, R, or O. In the second position, we only have 2 to pick from because we've already used up one of the letters. And in the third position, there's only 1 left over. So we get 6. Now, what if the word was oof? How many ways are there to rearrange the letters of this word? Well, we can see there's 2 letters that are the same, and so there's going to be a fewer number of ways to rearrange them. Obviously, we can use oof, we could do foo, and we can do ofo, and that's it. There are 3 other ways to rearrange them, but they just result in the same word. We could switch the 2 O's here and just get oof again, but the O's have been switched. We could do foo again, but the O's have been switched. And we can do ofo again, but the O's have been switched. And we don't count those because they're just duplicates. So in this case, there are still 3 possible positions to fill in. There's 3 letters we could put in the first, 2 in the second, 1 in the third, which gives us 6. But then we have to divide out the number of duplicates. In this case, we're actually going to divide by 2 factorial. 2 factorial is the number of ways to rearrange those O's. And then we get 3. So for the word match, there are 5 positions to fill in. We can put one of 5 letters in the first, one of 4 letters in the second, one of 3 in the third, and then 2, and then 1. So that gives us, what is that, 120? Yeah, 120. Any questions about that? Okay, number 8. The Spotify playlist has 13 songs in it. You want to play it with the shuffle option, which randomizes the order, and then you just listen to the first 8 of them. How many different ways are there for the songs to be presented to you? So you can solve this problem in much the same way. There are 13 possible songs, and you're going to listen to 8 of them. So there's 8 positions to fill. This is the first song, this is the second one, this is the third, fourth, fifth, and so forth. So there's 13 possible songs that would play first. There's 12 that would play second, 11 that could play third. We're assuming here that Spotify is not going to play the same song again. Like, it's not going to duplicate the songs. Then 10, then 9, 8, 7, and 6. So if we just multiply those together, we'll get our answer. Let me go ahead and do that. 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 is 51,891,840. So that's the answer we would enter here. But there's a formula for doing permutations. And you've probably seen that formula. The number of permutations given a number n, which is how many you're picking from, and then r, which is how many you're picking out of that set. So you're picking r items out of a set of n items. And the formula is n factorial over n minus r factorial. And so we can plug these numbers into this formula and see that we get the same thing. 13 factorial divided by 13 minus 8 factorial. That's 13 factorial over 5 factorial. And if your calculator can handle those numbers as integers, so they don't go into a floating point world where numbers are getting rounded. So if you can handle the numbers as integers, then you can plug it into your calculator or computer and come up with the answer. But what is this formula doing? So really, this formula is actually just doing this calculation. Because I can write it out like this. I can do 13 times 12 times 11 times 10 times 9. You can see that this product up here that I've circled looks a lot like the way you calculate factorial. It's just some of it's been chopped off. And so in order to get to this set of numbers, 13 down to 6, what I have to do is I have to chop off the 5, 4, 3, 2, 1 from the 13 factorial. And the way to get rid of those, the way to get those to cancel out, is to divide by 5 factorial. And when you do that, the 5 goes away, the 4 goes away, the 3 goes away, the 2 goes away, and the 1 goes away. And those all simplify just down to 1. So I want to emphasize here that permutations as a concept means to come up with all the different ways to rearrange a set of things, but the order matters. Permutations is not this formula. This formula just helps you solve the problem, but that is not what permutations are. And you can see that all this formula is doing is just simply doing a factorial across the top and then getting a bunch of those terms to just go away. Okay, so I don't want you to fall into this false belief that this formula is what permutations are. No, that formula is just an algorithm for helping you solve the problem. Once you understand what the problem is, then you can even solve it without using that formula. All you have to do is just do this multiplication. You know, it's a little bit tedious, but you can do it if you understand what the concept is. So in combinations, those are similar to permutations, but now the order does not matter. So there's no concept of a first thing and a second thing and a third thing. So in question number 9, the United States Senate, which has 100 members, is forming a committee with 8 senators. How many possible committees are there? How many ways are there to rearrange all the people to make committees out of them? But in this case, the order doesn't matter. There's no like first person in the committee and second person in the committee. It's just a set of 8 people in the committee. So we can actually solve this problem in much the same way we did with that rearrange the letters. We're going to come up with all the different ways there are to arrange the people in the committee, but then we're going to divide out the duplicates so that we don't end up with the same committee being listed multiple times. Okay, so we've got 8 senators. 2, 3, 4, 5, 6, 7, 8. And we want to fill up these slots. So there's 100 possible people we could put in that first slot. There's 99 in the second, 98, 97, 96, 95, 94, 93. All we have to do is just multiply those together. But then we need to divide by the number of ways that we could rearrange those 8 people. Right, so this is what we got on the screen so far is just the number of ways that we could pull 8 people out of a set of 100, but their order would matter. There's a first person and a second person and a third person all the way down the line. But because we can rearrange those 8 people and they're still the same committee, we need to divide by all the possible ways there are to rearrange 8 people. Just like there are 5 factorial ways to rearrange all the letters in the word match. We're going to divide by all the ways to rearrange these 8 people. And that's what the combinations formula is. It's basically the permutations formula, but with this additional term to divide by the number of ways to rearrange the people in the set. So if you want to pick R items out of a set of N items where the order does not matter, then you use basically the permutations formula, but divided by the number of ways to rearrange those R items in the set. That gives us N factorial over N minus R factorial. That's the permutations formula. And then a divide by R factorial. So in our case, we get 100 factorial divided by 92 factorial, and then 8 factorial. I'm not quite sure if my calculator can handle that, but let's give it a try. 100 factorial. Oh, see, it went into floating point world, so it wasn't able to do that. So the way we're going to have to solve this problem is just go ahead and multiply these numbers together and then divide by 8 factorial. So 8 factorial we can do. That's 40,320. But we're going to have to basically see this right here, that calculation. We can do it just by multiplying these numbers together. So we have 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93. Uh-oh. Well, it went into a floating point world there. Oh, but even if you divide by the 8 factorial, it comes back into integer world. So I think I'm good with that. So let's write that down. So this is 186 billion, 87,894,300. All right, how are we doing so far? Question number 10. In the dice game of Yahtzee, which I love playing with my wife, 5 dice are rolled and the values that come up are given a score based upon which numbers are showing. This is a very simplified version of the game. How many ways are there to roll a full house? And here I'm going to say that a full house is 3 of one value and 2 of another. So for example, if I roll those 5 dice, and I get like 4 here, and 2 here, and 2 here, and 4 here, and 4 here, that's a full house because I've got 3 of one kind and 2 of another. How many ways are there to roll a full house? So this is a combinations problem because the order of the dice doesn't matter. If I rolled those same 5 dice again and I came up with 3 4s and 2 2s, but in a different order, that would still be the full house. That would still be the same full house as the one I've got on the screen here. So the order of the dice doesn't matter. This problem can be solved using the combinations formula, but not directly. Still got to do a little bit of thinking to figure this one out. So although we do have the combinations formula, I actually wouldn't approach it with that. It actually makes the problem more complicated. So here's how I would tackle that problem. I've got 5 dice positions to fill. Now the order doesn't matter. So I'm just going to ignore the order and say that the first 3 dice need to be the same and the second 2 dice need to be the same. I'm just going to group them into a group of 3 and a group of 2. So how many combinations or how many ways are there to represent that first group of dice? Well, there's 6 possible numbers that could be in that first position. And the second and the third positions have to match. So there's only one possible value for the other 2 positions. And then for the grouping of 2, there's only 5 possibilities there because we already used up one of the dice for the first 3. And then there's 1 left for that remaining position because it has to match that 4th position. So 6 times 1 times 1 times 5 times 1 gives us 30. So the key thing to solving this problem is to realize that those 5 dice have to be broken up into a group of 3 and a group of 2. And within those groupings of 3, they all have to match. And within that grouping of 2, they have to match. Now, it doesn't matter which order I put that group of 3. I could put the group of 3 second. I could put the group of 2 first. It's still the same full house. I could interleave them together. Still the same full house. So I'm not, in this case, I'm not considering order in this case by looking at it as the dice have to be in one specific order. 3, 3, 3, or I should say a group of 3 and then a group of 2. And that takes into account that they could be in any order at all, by basically ignoring the ordering and saying there's only one ordering. There have to be a group of 3 and then a group of 2. Now, I've given this problem out many times over the years, and I always get some students who say the answer can't possibly be 30. It's got to be more than 30. I mean, it just seems like there would be more than 30. And the way to solve this is actually just to write a program. You could write a program that comes with all the possible rollings of the dice. What are all the ways to roll the dice? Which is 6 times 6 times 6 times 6 times 6. And then figure out of those, which of them are full houses. And then of those, how many distinct full houses are there? So I think you do come up with something like 300 or so full houses. But then when you eliminate the duplicates, it only just comes down to 30. So I would encourage you, if you don't believe or some of these answers don't seem intuitive, go ahead and write a program. That's a really good challenge. Write a program to directly solve the problem by just working through, brute forcing your way through all the possibilities, and then count up how many answers do you get that meet the criteria. I also say when I wrote this program to do this, the task of just rolling the dice, that was the easy part. That was just 5 nested loops. But then the problem of trying to figure out which of those combinations are a full house and then which of them are duplicates, that was the more challenging part of the program. So I would really encourage you to try to write that program if you possibly can. Max says he really loves the content of this chapter because these are the types of problems that get asked on things like technical interviews. Can you kind of reason your way through these even if you don't remember those combination and permutations formulas? And then so it's great to see all the patterns you see in between them. Yeah, technical interviews often have questions like this. Now, I have a thing against the technical interview questions that use brain teaser problems. Like a typical one is, can you calculate how many, let's say, gas stations there are in your city? They want to think about, like, how do you reason through a problem like that? But does that have anything to do with your job? If your job is, of course, to estimate the number of gas stations in the city, well, then sure, that's a perfectly valid question. But if you're like a programmer and you're doing, business logic, I don't know if that's a valid question to ask. Nevertheless, I can see the value in trying to figure out, how can you reason your way through that problem in the face of a bunch of ambiguity. Nevertheless, being able to calculate combinations and permutations, I think, is important for a computer programmer because you do run into those types of situations where you have to maybe establish an upper bound on how difficult this problem is to do, or like if you wanted to know what are the total number of possible passwords someone could pick from, that would be a useful thing to know, because if somebody wanted to break those passwords, you'd have to know how much effort would they have to go into it. We did a problem like that a couple weeks ago, where we tried to figure out how many 8-letter passwords are there, number 9, how many 9-letter passwords are there. That's kind of like combinations and permutations problems. You know, and now I'm looking at a YouTube comment here. You're right, some of these questions here do kind of assume that you know something about poker or Yahtzee. So Yahtzee is a simple, almost like a kid's dice game that's very similar to poker, but played with dice instead of cards. And so you roll 5 dice, and there's more complicated rules than just simply rolling the dice and looking at them. But basically, you roll 5 dice, and you look at the combinations of numbers that came up. And there's different ones you can get. Like you can do a straight. A straight means you have numbers that are all in a sequence, like 1, 2, 3, 4, 5, or 2, 3, 4, 5, 6. You've got you know, pairs of numbers, like how many 2s do you have, how many 3s you have. You have what's called a Yahtzee, which means all the dice came up the same. So you got 3s across, or 5s all the way across. And then you got full house, which is you got 3 of one value and 2 of another. So you've got like 1, 1, 1, and then 4 and 4, or 6, 6, 6, and then 2 and 2. But the order of the dice doesn't matter. You're just going to throw the dice on the board, and then you're going to look at the dice, and so they're just scattered around the board, so the order doesn't matter. So 6, 6, 6, 2, 2 is the same as 2, 2, 6, 6, 6, and that's the same as 6, 2, 6, 2, 6, right? So the order of the dice doesn't matter. And then there's always the Yahtzee player says, well, technically, if I rolled all 5s, that's also a full house, right? Because I've got 3 5s and then I've got 2 5s. But I'm saying for this problem, I'm going to simplify it a little bit and say a full house is you've got 3 of one and then 2 of a different value. Okay, we're almost at the end. So now we're at the section called the pigeonhole principle. So in the pigeonhole principle, the concept is you've got this like row of pigeonholes where pigeons can fly into them, and the pigeons don't like to be in a hole with another one. So if you were to release a whole bunch of pigeons and they were to fly to their home, then one pigeon would, I can't draw pigeons here, so I'll just say there's one pigeon here, and then another one will go into this one, another one will go here, another one will go here, another will go here, another will go here, here, and then here. And then finally, if there's a 9th pigeon, now they're forced to share. And so you'll get, at least one hole with a duplicate pigeon in it, or not duplicate, 2 pigeons in it. So they would prefer to be in a pigeonhole by themselves, but if they have to double up, then they will. So this is called the pigeonhole principle. You'll be able to fill up all the pigeonholes separately, and then finally you'll reach a threshold, a point at which the pigeons must double up, and they must go into the same pigeonhole. So this is not a problem of probability, like how likely is it that 2 pigeons will end up in the same hole. What we're looking for is a guarantee. In this particular diagram here, we are guaranteed that it will take at least 9 pigeons before there's a duplicate. Okay, it's possible that all 8 will fly into the same hole, but we're looking for what I would call maximally unlucky. To be maximally unlucky, all the pigeons are going to fly into separate pigeonholes, and then it's only on the 9th one when we'll get a duplicate. Sure, in reality, we might get a duplicate before then, but we're looking at being maximally unlucky. They all fly into separate ones, and then on the 9th one, we are guaranteed that there will be a duplicate at that point. Take it to the bank, guaranteed. Someone says, Zosi says, it's kind of like getting on a bus, right? Everyone wants to sit in their own seat. So how many people will get onto that bus before there's a guarantee that 2 people have to share a seat? I'm assuming people don't stand up, right? So everyone's going to want to scatter around the bus and try to sit in their own separate seats. And it's until the bus is completely full that you finally get two people that have to share. So question number 11. A bag contains a mixture of 30 apples, 30 bananas, 30 pears, and 30 oranges. Every minute you pick out one fruit. How long will it take you to ensure that you have at least a dozen of any one kind? Okay, let's read that carefully there. How long will it take to ensure that you have at least a dozen of any one kind? So we're not asking here, how long will it take before we have a dozen of all the kinds? How long will it take before you have a dozen of at least one of the kinds? So imagine you've got a bag full of fruit. There's a total of 120 fruit in this bag. Every minute you pull out one of the fruit at random. How long will it take you before you are guaranteed, absolutely guaranteed, to have at least a dozen of any one kind? So you could get maximally lucky and pull out an apple, and then another apple, and an apple, and an apple, and an apple, and then finally on that 12th pull, you pull out the 12th apple, and now you're done. You've now got a dozen apples, and so you've met the criteria. You've got a dozen of at least one of the kinds. But that's being maximally lucky, that you happen to pull out 12 apples in a row. How could you be maximally unlucky? The Lord Milbury says 45 minutes, and that's correct. 45 minutes. So how do we get that answer? So to be maximally unlucky, you could pull out an apple, and then an apple, and another apple, 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 apple. You pull out a total of 11 apples, and now you don't have a dozen apples. So you don't have a dozen of one kind. But now you start pulling out fruit again, and now you got bananas. And you pulled out 11 of those. You still don't have a dozen of any one kind, but now you've pulled out 22 fruit. And then pears. You got 11 of those. And then oranges. And you got 11 of those. So now you've 44 minutes have gone by. You've pulled out a total of 44 fruit, and you still don't have a dozen of any of them. So now you've been maximally unlucky. You have picked the fruit so that you don't meet your criteria for as long as possible. But now we've reached the point where no matter what fruit we pick out next, could be an apple, could be a pear, could be an orange, could be a banana, on the very next fruit we are guaranteed to have a dozen of at least one of them. So if we pull out an apple, we'll now have a dozen apples. If we pull out an orange, we'll now have a dozen oranges. So what we're looking for with these pigeonhole problems is, where's that dividing line? Where's that threshold between we don't meet the criteria, and then finally on the very next one, we do meet it? 11 plus 11 plus 11 plus 11 gives us a total of 44. And then on that very next one, "45 minutes will go by, and now we are guaranteed to have a dozen of at least one kind." Sure, we might have gotten lucky. It might have happened earlier. But by the time we get to 45 minutes, it's a guarantee. Right. Worst case scenario is what we're looking for here. What's the worst case scenario? How long can we go before we finally get to the criteria we're looking for? And then last problem. How many people are needed to guarantee that at least 2 of them have birthdays in the same month? Okay, you might leap at this and think, oh, I've heard about this birthday problem before. This is not the same thing. It's similar, but it's not the same thing. In that birthday problem, the question is, what's the probability that 2 people in the same room have the same birthday? That's a probability question. This is a guarantee worst case scenario problem. How many people do you need in that room to guarantee that at least 2 of them have birthdays in the same month?
Do we have to take into account leap years?
Yes, doesn't matter in this case. So some people would have a birthday in January. Some people would have a birthday in February. Some people would have a birthday in March. Some in April. Some in May. What's the worst case scenario? So we're looking for 2 birthdays in the same month. So the worst case scenario is one person has a birthday in January, one has one in February, one has a March, one has an April, one has a May, one has a June, one has a July, an August, September, and October, and November, and December. So at this point, we've got 12 people in the room, and we don't have 2 of them with the same birthday in the same month. Everyone's got a birthday in different months. But on the very next person, no matter what month their birthday falls on, whether it's September or January or April, we are guaranteed at this point that 2 of them, 2 people will have a birthday in the same month. So if on that 13th person, that person has their birthday in April, well, now we've got 2. And we've met the criteria that 2 people have a birthday in the same month. So with 13 people, we are guaranteed that at least 2 of them will have a birthday in the same month. Could it happen with only 2 people? Sure, but it's not a guarantee. If you pick 2 people at random, are we guaranteed that they'll have the same birthday in the same month? They'll have a birthday in the same month? No. How about 3 people? Are we guaranteed that we'll have at least 2 of them having the birthday in the same month? No, right? It's all going to be different months. How about 4 people? Are we guaranteed? No. And so we can state that same thing all the way up to 12 people. We don't have a guarantee at all that even with 12 people, that 2 of them will have birthdays in the same month. But on that 13th person, we must absolutely have at least 2 people with birthdays in the same month. It's a guarantee at that point. Does that make sense? Yeah, easy concept, but difficult to grasp sometimes. Okay, let's go ahead and check these answers. And what did we get? 12 out of 12. Excellent. Okay, so those were the practice problems. We just did these. So for homework, you're going to do these 10 problems here. Now what I've done here is I have amassed a collection of, this is kind of like a combinations problem, right? So I've amassed a collection of about 30 problems, and I'm picking 10 of them at random. So every time you take this, you will get a different set of questions. You can do this as many times as you want. So every time you do this set of problems, every time you do this, you'll get a different set of problems. There's no time limit, and you can take this as many times as you want. The goal is to get to 10 on this, so that you'll get full credit for it. So, like question number 1. Looks familiar. How many distinct ways are there to rearrange the letters in the word papers? So here's what I'm going to do. Why don't you go ahead, if you're following along on Zoom, go ahead and try these problems. And if you run into difficulty, just speak up and we'll work on the problem. For those of you who are on YouTube, I think what I'll do is I'll kind of like scroll through the problems, and then I'll just go through them one at a time. And then maybe what you could do is you might be able to do like screenshots as I go through the problems, so that you'll have all of them in front of you, and then you can work through those as well. So here is problem number 1. Here's problem number 2. Give you enough time to take a screenshot. On to problem number 3. I'm going to zoom in so you can see them better. So let me go back to the previous problem so you can see that one better. Here we go. And the next one. And then the next one. And question number 6. Question number 7. Question number 7 says, how many ways are there to completely fill a tic-tac-toe board? Now, in other parts of the world, this might be called knots and crosses. So I can draw a picture of it. You've probably seen a game like this. You know, you're filling it with X's and O's. And you're trying to get 3 in a row. So the question is, how many ways are there to completely fill up this board? So not how many ways are there to win, not how many ways are there to, you know, get 3 in a row, but basically how many ways are there to fill up this board with X's and O's. In the game, X always goes first. Okay, next question. And then question number 9. And then the last question. So again, if you're one of my students, there's an actual assignment for you to do. You'll get a different set of questions every time you take this, and the goal is to get them all correct, so you get a score of 10. Then it'll mark you as complete. So take some time to start working on these, and then if you run into some difficulties, just speak up and we'll maybe work it out for you. So what I'm going to do is I'm going to pause the Zoom recording so that people who are watching Zoom don't just see a whole bunch of us doing nothing.
Recording stopped.
Okay, well, all my Zoom folks dropped off, so they're not here anymore. So it's just you and I, YouTube folks. Does my LMS allow me to create programmable questions? Well, in the sense that like all these questions I have that have random numbers in them, I can then use the LMS will calculate the answer. So if I can plug in a formula that'll calculate the answer, that I can check that. What it doesn't allow me to do that I really wish it did was to be able to apply criteria. So for example, when I'm doing these problems, let's say I want to come up with 2 numbers in the problems, but I want to make sure that maybe when you add those 2 numbers together, they sum up to at least, let's say, 30. So I want to apply a criteria to it. Randomly pick the numbers, but make sure that they add up to at least 30. Otherwise, reject them and do another one, do another set. And so it doesn't allow me to do that. So sometimes what I have to do is just apply the criteria to the first numbers, like make the first number be 15 to 20, and the second number needs to be between 20 and 30. And now I'm pretty much guaranteed that they're going to add up to at least 30. But that's not an ideal solution. Somebody did develop a plugin, kind of like a plugin for my browser that will recognize when I'm setting up a problem in Canvas or LMS, and then when it does that, it can kind of it can download the randomly chosen numbers and then adjust them and then re-upload those numbers back again. And so kind of almost got it there, and then you just write JavaScript code in order to establish the criteria for the numbers. And then also what I wish it would do is maybe I could give it a list of possible values to pick from, and then it will just insert those values into the question. That would allow me to produce, say, a list of words, and then insert those words into the problem. Or I could do something like have a list of possible phrases, and then I could construct different problems out of those phrases as well. That would be awesome. You know, then I can kind of like have a more general purpose problem generator where I've got, in this case, the phrases could also, could possibly almost be different questions, right? And then in order for it to generate or randomly choose questions, rather than having me have to go through and generate, let's say, 10 variations on the same question, I could just have this question generator that has a list of phrases or a list of actual sentences that I could insert in there, and then it would just build the questions for me. That would be like totally awesome. But I've talked to the developers and they said like, yeah, that would be really cool, and as a programmer I can totally see how that would be a very interesting problem to solve, but that is such like a small, really small use case amongst the millions of people that are using our product. And they said, yes, from a computer science perspective, that's like awesome, but it would just be too complicated for the average person to use. And I was like, yeah, but like, could that be hidden in like the advanced features of the quiz or something? He goes, we'll think about it, but again, we have 1,000 other things that we have to attend to, and that's just really low on our priority list. The other thing I've asked for is when I'm doing any kind of developing a page, we use, there's a simple like text editor that we use to just develop the content, and it works like a simple word processor, right? You've got bold and italic, and you can change the font size and the colors, and it's basically all just user interface buttons for HTML code, right? But as a programmer, I'm very used and very adept at typing in what's called Markdown, which is a simple way of putting symbols into your text that gets translated later on into the HTML code. And so I've asked the developers, like, can you possibly have, because you have an HTML mode where you can just type in and then select from the menu like how you want it styled, or you can switch over to raw HTML mode where you can actually just code in the HTML tags yourself. I was like, could you also have a Markdown mode? Because that would be totally awesome. And they said, yeah, but again, really small use case, like, only, less than like 5% of people would actually ever use this. And, so it's just not high on our priority list. And so what I've taken to sometimes is having a separate Markdown editor on my screen where I type up my page in Markdown code, and then I ask it, generate the HTML, and then I copy the HTML and then paste that into the raw HTML mode of Canvas, and then I've got my page that way. But now that requires kind of maintaining the document in two places, right? Once on my desktop with the raw source code, and then I have to remember that if I want to make changes to this page, I have to go back to my original source document, copy and paste the HTML into Canvas, and that's just a pain. It'd be really cool if they just had a Markdown mode, and then problem solved. And it's not really, to me, that hard, because there are editors out there that just, they do Markdown, right? So it's not like they have to code this up from scratch. They just need to add a mode to it. But again, really low on their priority list. So I'm kind of stuck there. Yeah, a Markdown parser should not be that hard to support, because there are open source ones out there that you can just plug in, basically, and they just work. But one thing I do like about canvas is at least they are open to user-suggested features. They have a whole section on their website for suggesting features and then voting on them. I think that's really awesome that they allow their users to participate in the process of making the product better. Now, that said, the voting process needs a lot of work because there are hundreds of feature requests submitted like every month. And so every month they open up the current feature requests to voting. And the problem is now you have to vote on hundreds of items. And so usually what happens is you go to and it doesn't show you them all at once, right? It just shows you a screenful at a time. So it shows you like 10 items and you vote on your favorite ones. And then you go to the next 10 and you vote on those. And by the time you get to like the third or fourth screen, you're like, oh man, it's just a lot of work, right? And so, you know, and also the way their voting works is it sorts the items by their current popularity. So the ones that already have some votes float to the top, which means that those are the first ones that other people are going to see, and so they're more likely to vote on them. And the ones that are towards the back, on at least the first pass, that didn't get any votes, those filter to the bottom and no one ever sees them. So it's kind of like luck whether the feature request you put in happened to float at the top when the voting started. And if it did, then it's going to get lots of votes. And if it didn't, it's going to get none. And that's like a total pain. So I do appreciate the work they're doing to make their users part of the process, but the voting system needs to have some work done to it to make it more fair. So this is like, you know, if you're designing a user interface, I mean, you know, really have people test it out. The other problem with their voting user interface is it doesn't tell you how many items there are in the list, right? All it does is it shows you 10 at a time, but it doesn't tell you how many there are total. So you start going into the first 10 and you vote on the ones you want. Then you go to the second 10 and you vote on those. And by the time you get to the third or fourth 10, you're like, how long is this going to go on? Like, are there 500 or are there 50? I don't know. And so you just give up after a certain amount of time because you have no idea how far into this tunnel you are. So fixes to that, I think, would be, first of all, show the items in random order all the time, so that even if you only look at 3 screenfuls of questions, at least you look at 30 random things to vote on, not just the 30 most popular ones. And also give some people an idea about how many there are, so that if they do want to work their way through the entire list, they have some notion of how many more they have to do, rather than just this unknown, like, there's more ahead, but we don't know how many. So that's the 2 things I would fix about their voting system. And unfortunately, I don't think it's a voting system that they developed themselves. It's probably ones that they got from some other company, and so it's up to that other company to fix their voting system. So yeah, whenever you're doing a voting system, make sure that you present the items that you voted on in random order, and give people, if you can't show them all at once, give people an idea about how many there are total, so that they have some idea about how much time to invest into it. I mean, I can see why they might want to have the more popular ones float to the top, so that the more popular ones people get to see. You know, but again, it means that if people don't work their way through the entire list and they only work their way through, let's say, 3 screenfuls, then you're only going to see the 30 most popular items, and you're not going to see the other items that might have a lot of merit, but no one ever sees because they floated to the bottom. So as somebody who has submitted things to this process, it was really frustrating to see, my idea, which people, so you submit a feature request, then there's a comment period where people can go and comment on it, and then there's a voting period. And so I got lots of comments from people saying, yeah, that's a great idea, you should totally do that. And then when it came up to voting, it just never floated to the top. So the first few people who voted never saw it, so it never got any votes, and so it never floated to the top, and so people just never saw it. And so that idea went poof, not going to get done. Abdul, which question are you referring to? Oh, the one that's on the screen? So this one that's on the screen, you got papers, let me move it down a bit, P-A-P-E-R-S. So you got 6 positions to fill. You could do 6 possible letters in the first, 5, and then 4, 3, 2, and 1. So there's 6 factorial ways to rearrange the letters. But then since the P is repeated, you can swap those P positions, and then it's still the same word. So you have to divide by 2 factorial. So 6 factorial is 720, and then 2 factorial, of course, is just 2, so we get 360. Oh yeah, in Python, there's no built-in factorial. You can't just put an exclamation mark after a number and have it evaluate that. But there is a factorial function that you can import from the math library. Want to go ahead and do that? Say new notebook. We can say from math import, let's just do star, and then we can do factorial 10, right? And the nice thing about Python is we can throw at it a big number, and it calculate that. So we can do factorial 6 divided by, and I would use integer division here. So 2 slashes, factorial 2, and we get 360. I don't think Python supports operator overloading. So unfortunately, I don't think we can define our own operator like exclamation mark and make a factorial out of that. Okay, here's another question. The DES hashing algorithm, this is a really interesting question actually here. The DES hashing algorithm produces a 56-bit hash. The estimated storage capacity of the internet is about 10 to the 24th bytes. I looked that up on Google. As of 2014, which is the latest value that I could find. I'm sure it's much larger now, but as of 2014, the estimated total storage capacity was about 10 to the 24th bytes. Assume the average file on the internet is about 100 kilobytes. So some are larger, some are smaller, but 100 would be an average. Is it guaranteed that at least 2 files somewhere on the internet have the same DES hash? True or false? Oh, why did I use 2 slashes on that last question? That was because if I just use the single slash, I'll probably still I end up with 360.0, which tells me that it's going into floating point realm, which means there's a possibility it might round the answer. But by using the 2 slashes, I do integer division, and it makes sure that the numerator and the denominator are calculated as integers, no matter how big they get, and I'll get an integer answer. Okay, so the DES hashing algorithm produces a 56-bit hash. There's 10 to the 24th bytes stored on the internet. Assume the average file is 100 kilobytes, which is 102,400 bytes. Is it guaranteed at least 2 files somewhere have the same hash? So let's see how we figure that out. So, remember hashing from, what was it, last week? Yeah, last week. You take a file, you run it through the DES algorithm, and you get a hash. 56 bits. So how many possible 56-bit hashes are there? So there's one way to figure out is there's 56 positions to fill. Each one of those can be either a 0 or a 1. So there are 2 to the 56th possible DES hashes. We can ask Python for that number. It's this giant number. And I think that works out to be about 7.205 times 10 to the 16th. And so what we want to know is the number of files out there larger than the number of possible hashes? Yes, now I see your comment here. Yes, exactly, that's right. Is the number of files larger than the number of possible hashes? So the next question is, how many files are there on the internet? So there's 10 to the 24th bytes, and there are, to calculate the number of files, we're going to divide by the average size of a file. So 10 to the 24th, which is that number, but then we're going to divide that by 102400, and we get that number. And I can see right now, just visually, this second number is bigger than this first number. You can see it's physically longer, so you know the number's bigger. So what we've got here is a set of files, and there's approximately 10 to the 19th files. And then we have number of hashes, which is approximately 10 to the 16th. And so this larger number of files is mapping onto a smaller number of hashes. And so by the pigeonhole principle, we actually use that phrase, right? By the pigeonhole principle, the number of, well, actually, I think a better way to phrase this, you want to answer this correctly, is to say the number of files is greater than the number of hashes. So, by the pigeonhole principle, at least two files must, sorry, I'm cramming it in the bottom here, must have the same hash. Oh boy, my handwriting got terrible at the end, but it's because my palm was cramped up down to the very bottom of the screen. So that's kind of an interesting little outcome there, that if we were to hash every single file on the internet, we would discover that at least two of them would have the same hash, and probably actually many more than that, because the difference in magnitude is about 10 to the third. So that's what, 1,000? So there's 1,000 times more files than there are hashes, which means that for any given hash, there's probably approximately 1,000 files out there that have that hash, give or take, a few. So I think that's a really interesting little outcome of that. And that's why we've gone up to larger hashes. That's why we're now using like 256-bit hashes and 128-bit hashes, because now the number of files that have the same hash is diminished greatly. Like, what if it's not 2 to the 56? What if we're using MD5, which is 2 to the 128th? So now we can see the number of MD5 hashes is much greater than the number of files. So it's very unlikely that two files will have the same hash. Now you might get to what's essentially the birthday problem. The birthday problem would say, what's the probability that there are two files out there somewhere that have the same hash? And we could calculate that. And we probably find the probability is pretty small, because the difference here in magnitude is huge. Oh, you're right. And we're also assuming that every file on the internet is completely unique, and there's no two files are the same. You're right, we're assuming that. The reality is there are a lot of files on the internet that are duplicates of each other. So yes, you're almost guaranteed that there are two files out there with the same hash, just because there are a lot of duplicate files. So here's another problem. In a certain small state, license plates consist of 5 characters, 1 or 2 letters from A, B, C, or D, followed by 3 or 4 digits to make a total of 5 characters. For example, A4845 or DA981 or AA146. How many total license plates are possible? Abdul, you got the right idea for solving the problem, but you're using 9s where you should use 10s because the digits could be zeros as well. I guess I didn't make that super clear. You ever notice that on some license plates that they've, you can have basically letters or numbers on a license plate. And usually the license plates come in a specific pattern. Like here in California, the license plates are a digit and then 3 letters and then three numbers. So it's always a number, 3 letters, and then 3 numbers. And they're about to run out. We're almost up. So they started at 1 AAA 000, and they just started going up from there. And we're already, I think we're in the, if we're not in the 9s already at that first digit, we're very close. I think I've seen 8Y as the first 2 characters on the license plate. So I know we're approaching the 9s. And then what are they going to do when they run out? Like once we get up to 9ZZZ999, what comes next? And so it's been, I think, I read a Wikipedia article about this, and so far nobody really knows what's going to happen next, because the Department of Motor Vehicles has kind of like kept it on wraps as to how the license plates are going to be arranged coming up. But if history is any precedent, then what's going to happen is they're probably going to switch the order around. So it's 3 digits, 3 letters, and then 1 single digit on the end, because they've done that in the past, where they started out with 3 letters and then 3 numbers. This was a long, long time ago, like 50 years ago. 3 letters and then 3 numbers. And then they ran out of those, so they just switched the order to be 3 numbers and then 3 letters. And then once they ran out of those, they switched to the current system, which is a digit and then 3 letters and then 3 numbers. And so again, if history is any example, they're going to reverse all of that and make 3 digits, 3 letters, and then a single number. Or they could switch it around to, it starts with a letter, and then 3 digits, and then 3 letters. They could do that as well. That would give them plenty of license plates to choose from. And then Abdul says in their country, they just added another digit, right? But on our license plates, they've maxed out the size. 7 is the most number they can hold. The license plates just simply do not have the space to hold an 8th on there. But I have noticed that, well, certainly there are certain 3-letter combinations that never come up. So in whatever algorithm they're using to produce license plates, they ensure that certain 3-letter words never appear. You can probably imagine what some of those are, right? But those never appear. Certain number combinations also never appear. So there are certain license plates that are just invalid license plates. And I think also they avoid producing license plates that would result in ambiguous interpretations. Like I think they avoid putting I's and 1's together on a license plate just because they look so similar to each other. And they also avoid putting O's and 0's on the same license plate, again, because they look similar to each other. I have seen O's and I have seen 0's, but I can't think of an instance where I saw both of those at the same time, or at least they were never next to each other. They never put an O and a 0 next to each other. They would always separate them. Yeah, so there are certain number combinations and certain letter combinations that never appear. And there are certain combinations of both that never appear adjacent to each other, just so that if somebody has to very quickly read a license plate number, there's no question as to what it could be. And of course, here in California, you can also customize your license plate. You can actually pick your own phrase or own words, and there that they allow just about anything. And so I think maybe the only thing they don't allow is a license plate that has the current pattern of number. So you can't like, I don't think I could pick 9ZZZ999 as my license plate. I don't think I can pick that. If I'm going to produce a custom license plate, I have to pick something that's distinctly different from the standard license plates. And that's just the license plate combinations for cars. Trucks have a different pattern to it, and commercial vehicles, business trucks, have a different pattern that they use. Motorcycles have a different pattern. And so every type of vehicle has its own pattern of letters and numbers. So essentially, at least here in California, just about every pattern is in use for some type of vehicle. So really, they do just allow any combinations of letters and numbers. It's just that different classes of vehicles have different patterns of license plates. Oh, there we go. Just give every car an IPv6 address and be done with it. Sure, that sounds practical. What was your license plate number? Oh, I don't remember. It was 26 characters long. But I do remember there was a colon in it somewhere. Oh, your question was, what about Unix time? Are they going to fix that? So the problem with Unix time is that on Unix systems, it was stored as a 32-bit integer with the number of seconds as a 32-bit integer starting with January 1st, 1970. So if you work out the math there, then somewhere in the year 2036, that number was going to roll over and go back to 0, essentially. And given the problems with Y2K, they recognized that this was going to be an issue 36 years later. And so most systems, and by most I mean every major operating system, as long as you've been keeping your operating system up to date over the last 10 or so years, then it should not be a problem because they've switched over to a 64-bit number. And so they basically kicked that problem way down the road, way, way, way down the road by millennia. And they've switched over to 64-bit numbers. So that problem has been solved by now. So if you have an operating system that is current, within the last 20 or so years, you should be good. So in what year will the 64-bit numbers finally roll over? Let's find out. I'm sure we can Google this, but 64-bit number, so we got 2 to the 64 number of seconds that we can represent. And then if we divide that by divide by 60, and then divide by 60 again, and then divide by 24, and then we'll just divide by 365. I know it's 365.25, but let's call it good enough. So that's the number of years that we can represent. And then if we take that number and we add it to 1970, which was when this whole clock thing started, then in the year, what is that? 584,942,419,325, we will finally have the same problem again, which was what do we do about the dates that'll roll over? So 584 billion years from now, they're going to have to bring some programmers out of stasis to solve this problem. I imagine those people will make a lot of money. Oh, there's that problem. The Earth will probably not be here when that happens. The sun will probably not be here either. Who knows? The universe might not even be here either. I mean, the universe is only 12 billion years old. What's the chances it's going to make it to 584 billion? I don't know. Nobody knows. Oh, but there's the problem. Just saying, well, we'll all be dead by that time, so it's not our problem. Well, you know, it's our children's problem, and our children's problem, and our children's problem. I mean, that's what they said in the 1960s and 1970s. They said, oh, you know, Y2K is 30 years off, so we don't have to solve that problem now. You know, and surely back then, they didn't have the resources to solve it, right? The computers didn't have that much storage, so certainly saving a couple of bytes to just hold a 2-digit year instead of a 4-digit year was significant back then. But now we have plenty of storage, and there's no reason to not address the problem. No reason to not address the problem as we approach the year 2000. But here, I don't know. Do we have to worry about this timestamp problem, given that it's not going to be a problem for another 500 billion years? Here's what I'm going to do. Since we're all just sitting here staring at me, I'm going to write that program to calculate the number of full houses in a Yahtzee. I'm just going to do it from scratch. I haven't done this program in several years, so let's tackle this. So when I'm doing a problem like this, I like to think about basically starting with the worst case scenario and then winnowing down the problem. So I could start by generating all the possible dice rolls and then essentially filter out the ones that don't match the criteria. And then continually, iteratively filter out more and more of them until I arrive at just the answer, or at least a way that I could just visually inspect the answer. Because I'm not necessarily hoping to just have the number spit out the number 30, but maybe it could enumerate all the possible dice rolls and then mark somehow which are the ones that are the ones we're interested in, and then I can just visually count them. So let's start with that. Let's just get it to produce a list of all the possible dice rolls. So let's make a function here called, I don't know, all dice. And we're going to build up a list of all the possible dice rolls. So let's see, how should we do this? I mean, I know we have all these functions at our disposal like map and filter, but I just want to solve the problem first. So I'm going to start with like 5 nested loops. That'll just very quickly get me to just produce all the possible dice rolls. And then I'll assemble each one of those maybe into a string or a number. I kind of like the idea of a string, because if I use a string, then I can index into the string directly and see what their values are. If I store it as a number, then if I want to look at a specific value in there, I have to do something fancy with like dividing and modulo. So it might be easier to deal with them as strings than as numbers. So let's do that. Let's go for A in range 1 to 10, 1 to 7, right? So that'll give me 1, 2, 3, 4, 5, and 6. And then for B in range 1 to 7. For C in range 1 to 7. For D in range 1 to 7. And then for E in range. So again, I'm not trying to get the program perfect, but I'm trying to, every time I run the program, just sort of make progress towards the solution. So here's what I would start with. I would just start with these loops, And then let's go ahead and just assemble that into the strings, and let's just print them out. Actually, let's just start by printing them out. Let's just go print A, B, C, D, and E, and let's just see what happens. All right, look at that. That's a big list. Okay, so that's all the possible dice rolls. But I don't want to just print out those 5 numbers. I want to construct a list out of this. So let's go, I don't know, rolls equals an empty array. And then let's get this not to print out the 5 numbers separately, but to actually assemble those numbers together. And so to do that, since they're all just digits right now, I need to convert each one of them into a corresponding character. So I think I can do that with, is it str? Well, let's try this. Let's go roll equals string of A, and then I can use, now I can use the plus to concatenate them together. So it's not going to add the numbers together, it's going to convert each one of them to strings and then concatenate them together. And let's just print out roll and see what we get. Okay, that's better. Okay, so now they're all scrunched together. Oh, you're right. We could use formatting strings, but I've already got it done now at this point. So let's just proceed from there. So usually the point is get it to work and then get it to work better. Let's just get it to work. So let's now assemble this into a string, into an array. So we'll rolls.append. Actually, the way you do it, maybe another idiomatic way to do it is like this. I think that works. Oh wait, now I'm confusing JavaScript and Java. I mean, now I'm confusing JavaScript and Python. I'll use .append here. Okay, and then when we're all done, we'll say return rolls. Okay, and then all dice. Boom. All right, we got a list. Okay, and I know it's a list because it starts with that bracket right there, and I got commas in between all of them. So I got a whole bunch of strings here, and they go all the way down. And it just goes dot, 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 right? There's too many to list out here. Okay, so I know that works. And let's go from CSCI 26, import. Oh, actually, let's not do the computer science 26 library there, because there is a filter and a map built in. It's just they're a little bit harder to use than the one that I wrote for you, but let's try to use it without that. Let's just use the built-in map and filter. So now I need a function called isFullHouse, given a roll, and I want it to return true or false whether this is a full house or not. So if it is a full house, it'll return true, and if it's not a full house, it'll return false. So the question is one of these rolls a full house or not? So how do we figure out whether a given roll is a full house? Well, one possibility is we could just count up how many times does the 1 appear, how many times does the 2 appear, how many times does the 3 appear, how many times does the 4 appear, and so forth. And then just make sure that the count of one of them is a 3, the count of another one is 2, and the others are all zeros. So why don't we do that? Again, the whole point here is just get it to work. This is called a one-off program, right? We're going to, once this program is working, we're going to run it once, we're going to get our answer, and then we're done, right? So really for me, because the number of possibilities is not too tremendously huge, overall efficiency is not my primary concern. What I'm mostly concerned about is, can I put into code my thought process, and does it produce the right answer? So I'm worried about accuracy, and is my thought process correct in thinking about how to solve the problem? Not necessarily in the most efficient way, but does it make sense? And so what I described was, let's just add up how many ones there are, how many twos there are, how many threes there are. Let's just do that, and then we'll see if there's 3 of one and 2 of another. So let's just add up the ones. We just have to do a loop. We go for D in roll. Remember, roll is a string, so D is going to be one of the dice within the roll. So we'll go ones equals 0. And then we'll go if D is equal to a 1, then increment ones. Okay, and then we'll do, actually, and we can do that for if D is equal to 2. Actually, let's just go 2's equals 0. I know we could use an array, but that's like an optimization on top of my thinking process here. So my thinking process is I'm going to have 5 variables, right? Again, this is not, I'm not trying to make a super scalable thing where I could have any number of dice. I'm trying to solve this one particular problem that has only 5 dice in it, which is why I'm using 5 separate variables, right? And I'm thinking, yeah, of course I could use an array here, but I've already started down this thinking process, so let me just take that to its conclusion, and then maybe later on I could modify it to use arrays. Or if I run into a situation where using 5 separate variables is just going to create a problem later on, then maybe I'll fix it. But right now, I'm going to try this out. I want to finish this up. Okay, so I have 5 separate variables that contains the number of 1s, 2s, 3s, 4s, and 5s. And now I want to know, are there exactly 3 of one and 2 of another? Well, this, I mean, I could do some really large if-else on here. How about this? How about this? We could say, like, if 1s is equal to 3, or 2s is equal to 3, or 3s is equal to 3. Whoops, not those symbols. Or. I gotta use the word or. Or 4s is equal to 3, or 5s is equal to 3. And 1s is equal to 2, or 2s is equal to 2, or 3s is equal to 2, or 4s is equal to 2, or 5s is equal to 2. Will that work? Then return true, else return false. Actually, so this is basically return this. All right, so is that going to work? Let's try it out. Let's just go is full house. 1, 2, 3, 4, 5. Okay, that's false, right? That's good. How about 1, 2, 2, 2, 3? Okay, that's false. Is full house 1, 1, 2, 2, 2? Right, that's true. So what I'm trying to do here is I'm trying to figure out, is there some dice roll combination I can give it that is not a full house, but the function thinks that it is? Let's try 1, 2, 1, 2, 1, 2, or 1, 2, 1, 2, 1. Okay, that is a full house. How about 2, 2, 4, 4, 5? Okay, so far this seems to be working. What about 0, 0, 0, 0? Okay, that says false. Oh, how about all ones? Is full house. Okay, that says false because the number of ones would be 5. So that's that for my purposes, that's not a full house. So a full house is 3 of one and 2 of another. So yeah, there are all sorts of optimizations I could do on this. I could use a dictionary, convert the string to an integer, and then use that and increment something in the dictionary. I could use any, but again, I was just going with, this is my line of reasoning. Sure, it resulted in some more typing, but as you can see, this function appears to be working, that no matter what value I throw at it, my line of reasoning here was sound as far as how to approach this problem. We could make it more compact, but this is a one-off program. I just want to see the answer at the end. How about 3 of a kind that isn't a full house? I think I covered that here. I've got 3 2s and then a 1 and a 3. And so that's not a full house. Okay, so let's go. Filter is full house. And what did I call this thing up here? All dice. Okay, and so remember, I'm not using the library function that I wrote. I'm using the built-in one. The built-in one says it has applied the filter function to my isFullHouse function and the all dice, which produces a list, and it returns a filter object. And so it's not something that we can see. So what I have to do is I have to convert that filter object into something that I can see. And what I want is a list of the strings that met the criteria. So if I put list in front of that, then I now get a list of the strings that met the criteria. And so let's take a look at this. Is this a full house? Yep. I'm just visually inspecting to make sure that these things worked. Is this a full house? Yes. Is this a full house? That is. Yep. That is too. Right, let's just kind of randomly look at some other ones. That's a full house. How about this one here? Yep. This one looks good. Okay, that one's good. Okay, but you can see that there's more than 30 here. Right? How many do we have here? We've got, what's the length of that? Well, let's do this. Let's just assign this to a variable. So let's call this fh. So here's the value of fh. It's that thing. And I want to know how many are there. So the length of fh is 200. So there's 200 possible full houses. But I'm seeing here, you're right, 11133 is the same as 3311. So like, here's another example right here, these two. 11313 is the same as 11331. Those are the same full houses. So I need to eliminate those as duplicates. So if we've got our list now of all possible full houses. Now what we need to do is further condense that list and remove those duplicates. So what can we do there? How do we tackle that problem? How do we remove like this one and this one? And they're not necessarily going to be next to each other, right? We got 11333, and later on down the line, we're going to find that there's a 33111, right? So they're not necessarily going to be next to each other. Okay, it sounds like this could be a job for a set, right? Because set will eliminate duplicates. But if we throw these into a set, it's still going to see these as being the same thing, or different things, right? This one here, it's going to see as being different from this one down here. So we need to somehow say that these are actually the same thing. Someone says some kind of checksum. Sorting them? Can we do something with sorting them? Now, I mean, they're already sorted in order, right? They go from 1 up to 6, right? So they're already in numeric order. But can we do something with that? What if we sorted each one of these so that within the string, each one of them would be sorted in order, so they would go numerically within the string, right? And that would mean that these two here would become 4, 4, 4, 5, 5, and this one down here would also become 4, 4, 4, 5, 5. So if we sorted each one of the digits themselves, let's see, is there a built-in sort function? Ooh, no. It's not turning green, so I know there's not a built-in sort function. At least there's not one that lights up like that. Python sort a list. Oh, I see. It's a method. Ah, got it. Okay, so if I go like well, like let's just go. Let's do this. Let's go. If I do hello, that's a string, and I go dot sort. Oops, I can't do that. Oh, strings. Oh, strings can't be sorted. Which is funny because they're just arrays, right? I don't know why they can't be sorted. So here's what we can do. Let's make a function. Let's call this sort string. So we'll take that string, we'll convert it into a list, and then we'll sort the list, and then we'll reassemble it back into a string. Now, there might be a built-in function to do exactly this. Someone says sorted. Oh, sorted? What does sorted do? It lit up in green, so I know there's a built-in function. Sorted function returns a list of the... Okay, well, maybe that'll work. Let's try that out here. Sorted hello. Oh, hey, that almost worked, right? But it didn't produce a string. It produced a list of characters. But we can then take that and convert it back into a string. Oh, it didn't work. How do we do this? I think there's a method called join. No. Implode? No. Again, I think I've got my JavaScript or PHP messed up. Oh, gosh, that's horrible, right? Dot join sorted. Hello. Ah, there we go. Okay, so what that does is it takes the empty string and it applies the join method to it. And so we're using the empty string as the delimiter between the items that we're joining together. And then we're passing in as a parameter the list that we want to join together. This actually works exactly the opposite the way I thought it would work. I thought it would be like, take a list and then join, and you pass it the delimiter you want to use. Right, but that doesn't work. Yeah, so it goes the other way around. Is you use the delimiter has the join method, and then the items that you want to join together are the parameter to the join method. Oh, that's just exactly backwards in the way I think about it. But I think it'll work. So let's make a function called sort string. We pass it a string, and then we're going to return empty string dot join sorted s. Okay, and then if we go sort string and we pass it hello, then we get hello back. Good. And we pass it sort string and we pass it 11221, then we get 11122. Okay, so now I can go map sort string onto my list of full houses. And I get back a map object, but I want to convert that into a list. So let's go list of that thing. Okay, and that's good. Now we can see that every item in here has been sorted. So we got 11222, and right below it, we've got 11222, and then 11222, and 11222, and 11222. You can see all those duplicates in there. So now, instead of throwing it all into a list, let's throw it into a set. So it'll eliminate the duplicates. And look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait a minute. Where's the sixes? Oh, is my list doesn't go up to the sixes. What's wrong? Do you see the problem here? Right? I don't see any sixes in here, and there should be sixes. It goes up 1, 2, 3, 4, and then that's it. Okay, so something went wrong here. This list doesn't go up to, oh, it's my is full house function. See, in my is full house, I only went to 5s. Oh, well, that's easy to fix. And then over here, okay, so I got to do that one, and then these should all work, right? Let's make sure those all still work. Good, good, good. I'll throw in a 6 here. Good. So here's my list of all full houses. There's this. So my length is 300. That's actually what I expected. When I first got 200 out of that, I went, oh, that doesn't look right. I thought it was 300. Oh, can I make a new line after the or? Can I? You mean after the and? How do I do that? Because Python uses the end of line marker, the end of line character as the end of statement marker. So Python continue line. Oh, I got to use a backslash. Okay. Backslash. And is that better? So the way I did it is I put a backslash over here. That tells us that the line continues on the next line. Okay, so this works. Here's my list of full houses. There's 300 of them. Then here's my sort string. We're going to do this map right here. Oh, okay, good. Now we could just go, what's the, well, first of all, let's look at this. So we see we've got no duplicates in here. So here are all the possible full houses, but they've all been sorted. And then we could just count them up, right? There's a few enough there that we could just visually count them up. But I'm going to assign that to a variable. So here's the values. And then I can say, what's the length of that? And it says 30. So that's the answer I was looking for. There are 30 distinct full houses in a game of Yahtzee. So we had a way of doing it mathematically by just reasoning our way through how would we plug in the numbers and get an answer. And then we wrote a program to give us the answer. And so in a full house, there's no ordering, right? 3, 3, 3, 1, 1 is the same as 3, 1, 3, 1, 3, 1, or whatever. 3, 1, 3, 1, 3, right? Those are the same full houses. So all we wanted to know was how many distinct full houses are there, and there's 30. There's 300 full houses if the order of the dice matters, but in the game of Yahtzee, the order of the dice does not matter. So there's only 30 full houses. So basically, for every full house, there's 10, I guess there's 10 variations on it. So if you have 5, 5, 6, 6, 6, there's 10 ways to reorganize those 5s and 6s into other full houses that are the same full house. Oh, that was kind of cool. I like that. So we didn't write like one complete program. We don't have one program where we just run it and it just produces the answer. But we developed incrementally and taking advantage of the fact that in Python you can run a bit of the program, develop a bit of the program, run it, get an answer, and then go from there and do the rest of it. We built up that program from top to bottom. And then finally at the bottom, it gives us our answer. But again, we don't have one where we can just say, run it, and it gives us the answer. We could compose a function that does those same steps in order and gives us the answer 30, but this was a one-off program. All we were interested in is coming up with the answer, and we weren't interested in saving that as a separate program that we could run later on that would give us the same answer again, right? We might as well, now that we know the answer, we might as well do this. Might as well just say define distinct full house. Return 30, right? Because that's always going to be the answer. It's always going to be 30 for 5 dice that, you know, add up to have 6 as the possible values. It's always going to be 30. So there's kind of no reason for us to save this program because there's no variable input to it. Now, if we had a program, we want to write a program where it said you could play Yahtzee with up to 7 dice, and maybe a full house would be 4 of one and 3 of another, or you could play with 9 dice and there'd be 5 of one and 4 of another, right? Now you've got kind of like a problem that has multiple solutions based upon the size of the problem. Then we could write a program that we might want to save away and be able to compute the answer for any number of dice, I guess as long as they're odd. But here, for the game of Yahtzee, that's played with 5 dice, they each have 1 through 6 on them, the answer is 30. Yahtzee's really easy to learn, right? It's basically a kid's game, or it's a game where you can play it with a group of, you know, up to 4 or 5 people, and you know, no one's really thinking that hard about it. It's kind of like a party game in that case, but it's great for kids because it gets them kind of thinking about dice combinations and adding things up and doing a little bit of arithmetic to come up with your final score at the end. Oh, you can calculate the possibility that you have a full house. Sure. I mean, we know that the length of full house is 300. Oh, that's the length of full house. And all dice, we could say, what's the length of all dice? There's 7,776 ways to roll the 5 dice. So the probability of getting a full house, it would be, was it 300 divided by 7,776? So there's just about a 4% chance of rolling a full house on any given dice roll where you roll all 5 dice. That's not too bad. 4% chance. Always seems higher than that. When I'm actually playing the game of Yahtzee, it always seems like if I roll full houses more often than that. More often out of every 1 in every 25 rolls, I get a full house. Seems like I get it quite a bit. More than 1 out of every 25, but I'm probably just imagining things. Okay, so if you wanted to see how we did that piecewise, the first thing we did, oh, that's different stuff up here, is we came up with a function I called all dice that just produces a list of all the possible dice rolls. And then I made a function called isFullHouse that given a specific dice roll tells you whether or not it's a full house. And we did it by summing up the number of 1s and the number of 2s, the number of 3s, and so forth, and then just making sure that you've got 3 of one and 2 of another. We tested each function as we went along. Then we applied, or we used the filter function to filter the all dice with whether or not it's a full house, converted that to a list, and that gives us a list of all possible full houses. Then we calculated how many there are. And then we learned how to sort a string. So given a string, you can then sort each element of the string and you get a list of characters. So then to turn it back into a string, we have to use this weird join method on the empty string. Oh, by the way, you know, you can put something else in here. You can put like, Let's put an exclamation mark in there. And then what you get is you get an exclamation mark in between each letter. So this is the delimiter, and this is the elements we want to join together, which, as I said, works in the exact opposite way than I would expect. To me, that just looks weird. What I want to be able to do is I want to be able to say sorted hello dot join. And then if I don't pass in a delimiter, then it just joins them together. If I do pass in a delimiter, then it uses that as a delimiter. That would make sense to me. As a programmer, that would make sense. But for the Python people, that didn't make sense. So I don't know why. That's crazy. Anyway, so I made a function called sortString. You give it a string, and then it just sorts the element, or sorts the characters and returns the string. And then we use map to map that function onto our list of full houses. We threw it all into a set, and that had the effect of removing the duplicates. And then we just find out how long that set is, and we got our answer. Yeah, Python is a language that has evolved over the years, and it does have a lot of inconsistencies. I do like it for its simple syntax, and I dislike it for its inconsistent use of methods in one place, functions in another, and inconsistencies even within the same library. It's all because it just, it evolved organically out of what used to be a really simple language that, met a specific goal, and then stuff got added on over the years. That's just a kind of a problem with languages in general, is that happens. And of course, Python 3 was almost an attempt to kind of go through there and remove some of those inconsistencies. But if you remove the inconsistencies, like you change the way the join method works, well, then all sorts of stuff breaks, right? All sorts of code that used to work under Python 2 no longer works under Python 3, and you want to eliminate that as much as possible. There was another language called Perl that kind of went through the same thing. There was Perl version 1 and version 2, and they got up to version 5, and everything was great. As they went on, they added new features to the language, but they kept it backwards compatible for the most part with the previous versions. But then along came version 6 of Perl, and that was a completely different animal. To the point where Perl 5 programs wouldn't necessarily run under Perl 6 because the syntax was different in some cases. So they came up with a converter program. You could run your Perl 5 program through this converter, and it would turn it into a Perl 6 program. But it meant that you couldn't go backwards necessarily. You couldn't take the 6 program and roll it back into a 5 program. Maybe Python should have done the same thing there. They should have like a Python 2 to Python 3 converter, and then really made a good cut and say, okay, Python 3, we're going to remove those inconsistencies. We'll make the language nice and consistent throughout, but it means your Python 2 programs are not going to work. So you're going to have to run it through a converter to turn it into a Python 3 program. But they elected not to do that. They did say that your program's not going to work. Here's how you fix it manually. Like, go through your Python 2 program, and here's some things that need to be fixed. But a lot of these inconsistencies are still there, so that programmers wouldn't have to make too many changes to their program. So maybe Lord Melbury says, I'm enjoying learning C. Maybe think about how you could solve that same problem, but in C. Now in C, you don't have sets, all you have are arrays, and you don't have a nice map and filter, but maybe you could write your own, or you could just figure out, how can I solve this problem without those functions? I always think that's a good programming challenge. Solve a problem in one language, and then try to solve the same problem in a different language. And you can really see how those two languages really have different pros and cons and different kinds of problems that they happen to be good at solving. There are certainly programs that C is good at that Python's probably not as good at. Okay, well, I had a lot of fun today. I had a lot of fun writing that program. It was good to revisit that after a couple of years. And this time around, I used map and filter, which I didn't do the last time I wrote it. Last time I wrote it, I essentially wrote my own map and filter by, it would take in a list and then it would just build a new list based upon the criteria of the original list. That's basically what filter does. And then map, I would essentially just take a list coming in and then apply a function to it and build a new list as it came out. Or I would just transform the original list. So this was nice and modular. I was able to then write functions, test each function out separately, and then use those functions as part of the greater solution. I really like that. Okay. Well, I lost my Zoom folks a long time ago. So hopefully they'll watch the video. And oh, actually, I lost them a long time ago, and I paused the Zoom, and I never unpaused it, so they didn't see any of this. The YouTube folks, you got all this stuff. Okay, well, I'm going to go ahead and end the Zoom thing since I just paused on it anyway. Actually, here's what I'll do. I'm going to cancel that. I'm going to unpause it, say goodbye to the people on the video, and then come back to you.
Recording in progress.
Okay, we didn't get very many questions on that, so what I would encourage you to do if you're watching the Zoom video is actually watch the YouTube video, which includes some content, actually about an hour's worth of content that is not on the Zoom video. So you might want to switch over to that one, skip ahead to about an hour and a half into the video, and then start watching from there to see a lot more content that wasn't in the Zoom video. I forgot to unpause the Zoom video. So I will say goodbye for this one, and I will see you on Monday. We're going to be starting in on discrete probability. So now we're going to actually calculate what are the chances, what's the probability that something's going to happen. When we were doing the combinations and permutations, we're asking how many ways are there? And from that, we can compute probabilities. Like once we know how many ways there are to, let's say, roll a full house, then we can compute the probability of rolling a full house once we have those numbers. So that's kind of what we'll start doing next time. So that'll take up, I think, both sessions next week. So it'll be Monday and Wednesday, discrete probability. Along the way, we'll learn how spam filters work. So that's going to be really great, great practical example of how we use the probability to do something that we all use every day. So have a good weekend, everyone. And I hope you have a great next few days to work on your assignments and catch up. And then I will see you on Monday. Take care. Bye-bye. And then YouTube folks, I will see you on Monday as well, or tomorrow for the C programming class, where we're going to do some more with files, and then we're going to start on hashing and password cracking, but written in C instead of written in Python. Okay. Have a good day, y'all. It was good chatting with you, and I will see you later. Bye-bye.